About the end of the course. So I'm not assigning any more homework. I guess that there was none due today. All right, so that's fine. And that's it. So you've done your last homework already. I'm going to post the final exam, which will be a take-home sometime today. I have, probably it'll be tonight. And I'm open to discussion about how long you want to spend on it. I usually give the class a week. I tried to make it so that you could do it in something like between 5 and 10 hours of work. It's totally open in terms of you can use notes, books, internet, computers. The one thing that's not allowed is to collaborate. You're not supposed to ask anybody for help with the questions. If you need a clarification, you could ask me. The office hours with the TAs will stop during this time. So don't ask them anything. But otherwise, you can do whatever you want. Now, if you do copy something off the internet, like you find an answer to a question, I mean, hopefully you won't, but if you did find an answer somewhere on the internet, I guess it's possible, then be honest and say that you did that. You're allowed to do that, but you just have to admit it, otherwise it's plagiarism and would be, you know, bad violation of academic integrity. So, but as far as how long to take, so usually I give a week, like I say, and I figure it takes about 5 to 10 hours of work. The questions are, you know, more open-ended and longer than a usual homework question, but not much. And students have not complained about time pressure in the past, but I could give you longer than a week if some of you have deadlines or something. So on the other hand, if I give you longer than that, you might feel like then you have to work on it for 10 days, and maybe you don't want that feeling. Or maybe you're worried someone else will work on it for 10 days and you only have 5 days. Or, I don't care. You have an opinion? Too many deadlines before slope day. Okay. Yes, it can be any time we want. It's our course. We can do what we want. May 20th. Well, that would cause a little trouble because I have to grade it, and it will take me a while. I have another course that I have to grade where that final exam is May 17th. So I'd rather be done grading your test before May 17th. So one possibility would be if I gave it to you to return on something like, well, I'd be open to either May 9th or May 13th. If it was May 9th, that's a Friday. I had originally proposed May 6th, which is next Tuesday. So if it's May 9th, when is slope day? That's May 2nd, right? May 8th? A Thursday? That's weird. The one extra day makes a difference for you? No. How about we say what if we say May 13th? That would be 2 weeks. It will not take anywhere near 2 weeks of work. So do whatever other stuff you need to do, but leave some time to do this. The questions will require some thinking, and I actually want you to do... Some of the questions will be unlike homework questions where I will say something like, analyze this system. But I won't say more than that. So then you'll need to know, well, what does that mean? What kind of analysis should I do? Well, that's part of what you should have learned in this course. Okay, so you won't really know when to stop. Like you'll think, well, should I check the fixed points? Should I check their stability? Should I look for quasi-periodicity? Should I prove it has or doesn't have chaos? Do whatever you can do. Do whatever makes sense to you. Yes? Okay, to physically turn it in, I think I'll just be at my office on that day, and I'll give you like a 3-hour window to walk over and drop it. If for some reason you're out of town, I suppose you could scan it and send it to me as PDF, but normally people just bring it physically in person during a window of time. So, okay, so we converged on May 13th. All right, and I'll say it'll be, what's that? I guess it will be due, I don't know, like around lunchtime or something. I don't want it to be too early. Some of you may have exams. Should it, I don't know, does it matter when it's due? What time of day? No. All right, I'll just make it so you can get there. So, and then I'll, you know, oh, this is going to be on Piazza. You'll see the information in detail there. Any last minute question? Yes? Does the longer duration mean what? The test will be about like 5 questions or something. I haven't made it up yet, but it would be on the order of 5 or 6 questions, you know, of the type analyze this system. Some of them will be more specific, like more like homework questions, but some of them will be these open-ended things. I'll give you just a system to analyze. Okay. And you know, like I say, you're free to use computers. You will probably find it necessary to use a computer for parts of it. So if you've been avoiding that all semester, this would be a good time to learn how to integrate equations on a computer and plot the results, because you're going to have to print them out or copy them or something. Okay, so we'll say it's due May 13th. Okay, so let's, we have 3 lectures to go here, right? We have this lecture and 2 more. And so, well, today what I would like to do is, let's talk about chapters 11 and 12 in the book. We don't have enough time to give them thorough coverage. Remember where we are. We've been talking about chaos, first in the Lorenz system, then we talked about the period doubling root to chaos in the logistic map and its universal properties. But there are a few big things that we haven't really explained yet that I feel like I want to touch on. For instance, when we talked about the Lorenz system, we said that the trajectories were approaching, in the long run, this set that we call the strange attractor. But what is that thing, and what does it look like? We drew some computer graphics of it, but we didn't really get into much detail about the geometry of the strange attractor. And so I want to discuss that, because that was something that baffled people in the mid-1970s when chaos was really sort of extremely hot. And I think you'll find it interesting. So, okay, our topic then for today, and I think also for next lecture, will be picturing the geometry of strange attractors. And then our final lecture will be about what chaos is good for in an engineering sense. Like, can you use it to do anything, or is it just an annoyance? And so that'll be how we'll end. All right, but anyway, so picturing the geometry of strange attractors. This will require us to talk about some ideas from fractals, and so I'll very lightly discuss fractals, but there is a whole chapter in the book about them, so you probably ought to take a look at both chapter 11 on fractals and chapter 12 on strange attractors. So, back to the Lorenz system and its strange attractor. There's one thing that really does seem quite paradoxical when you think about it, which is that we said a hallmark of chaos is that trajectories separate exponentially fast, right? When they're close together, they initially separate approximately exponentially, which we call sensitive dependence on initial conditions. And on the other hand, we said that the attractor lives in a bounded region. It can be enclosed in a certain big sphere, and so it's a bounded object, yet the trajectories are spreading apart from each other exponentially fast, and those sort of seem a little bit hard to reconcile. So let's just ask the question, how is it possible to expand endlessly but remain in a bounded region? As the distance between neighboring trajectories does. Now I'm exaggerating here. This is not really true. Of course, the neighboring trajectories can't get farther apart than the diameter of the attractor. So I really do mean something not quite as, this really would be paradoxical. But still, the question of repeated stretching and yet staying in the bounded region is what I want to think about in more detail. So one way to get intuition about this is to think about the geometry of what's happening in phase space. And the short answer would be that the process in phase space that causes this is a repeated stretching of the phase space, folding, and a process that people call reinjection. And so to clarify what those buzzwords mean, let me draw some pictures of a much more familiar thing that if you ever cook or bake or make pastry, not that I do, so I don't know anything about what I'm about to say here, but just pretending, little cooking example. Is what I'm told is a process for making pastry or croissant. That is going to take a blob of dough and then you get a rolling pin, right? And then you can roll the dough flat and stretch it out and make it long. So you flatten it by going in these directions, pressing down with the rolling pin, and you stretch in these directions. I mean, really, with that volume of dough, I guess it would be much longer than what I've shown. Maybe I'll indulge myself. Okay, if you're wondering what has happened to the professor, you know, what are we talking about? The dough is supposed to represent phase space. And the rolling pin and the flattening and the stretching is what the vector field does to a blob of initial conditions. Right? Remember, we've talked about this idea of a blob of an initial condition flows around to a new place, and then if you had a blob of them, then that blob will flow to a new blob. And so I'm claiming that in chaotic systems, it's important to think about flattening. That's associated with trajectories approaching an attractor. That's the compressing directions that you go onto the attractor. The stretching is what's happening on the attractor as nearby trajectories are getting stretched apart. Okay, so first we would take the dough, flatten it, stretch it, then fold it. That is, make it look something like this. If you're really thinking about dough in the kitchen, you really have rolled it out, you flatten it, and then you just fold it on top of itself to make something like that. And except there wouldn't be such a huge gap here, but just for visibility, you can see that it's folded. But really, they'd be pressed onto each other, those two layers. And then the reinjection step is to go back here, which means start all over again. That is, reinject this region into there where it can get subjected to another round of flattening, stretching, folding, and reinjection. And so we're going to do this many times. It'll be an iterated map on the dough. And to see what would happen, let's just think about one more step. Okay, you started with a block. It made this horseshoe shape. If you take the horseshoe, put it in here, hit it with the rolling pin, and then fold that thing, maybe you can visualize that the next iterate would look qualitatively like this. Kind of tricky to draw. Whoa. Now, that's a little hard to visualize. What did I just do? Let me fill it in. So there's dough. I realize it looks like a labyrinth. The black spots are just empty space. I don't know if this is even worth doing, but I'm almost done, so let me keep going. All right, whatever. You get the idea. So what I'm trying to convey here is that we started with something with one layer. After one folding, it has two layers. And now after the folded object got folded itself, it now has four layers. Right, you're doubling the number of layers with each iteration. And so you may know that there's this stuff called phyllo dough, or in French, millefeuille, or something. Sorry for the pronunciation. I see we have people who could pronounce it better. But anyway, that would mean 1,000 leaves or something, 1,000 sheets. And really, I guess it's 1024, right? 2 to the 10th if we did it 10 times. So anyway, the making of that kind of stuff involves this repeated folding. Okay, so the claim is that this flaky layered structure something like this is actually happening in the phase space of chaotic systems, not just in this cooking example. And so what I'm trying to hint at is that there's a mechanism through the way that we flow in the phase space of a chaotic system to automatically generate a fractal structure of attractors. That's one aspect of the intuition. We're going to go into it a little deeper in a minute. But another thing, if you believe this nonsense about what's happening in phase space, is that this would explain where chaos comes from, not just where the fractals come from. That is, if you imagine a little set of nearby initial conditions, like say, put some food coloring right here, put a little, needle and inject a syringe, fill a syringe with some blue food coloring, squirt that in there. That represents an initial condition and some nearby initial conditions. As you then start flattening it out and doing this process over and over, you could imagine that after 10 iterations, the food coloring would be sort of spread out pretty much throughout the dough, conveying the idea that the initial conditions that started close after enough time could end up almost, their trajectories could end up almost anywhere on the attractor. Yes? How distinct are the phases? You mean, can I see something that looks like this?
Kind of. I mean, are flattening, stretching, and reinjecting all happening at the same time? Or if you look at a given phase portrait, can you see like, oh, now it's stretching, now it's flattening?
Okay, so the question was, how distinct are these phases referring to the different processes taking place here? Is there a place where you can see the flattening and stretching happening, and then another place where the folding is happening? Yes, they are. There is a sense in which you can see that. And that'll become clear when I show this computer pictures in a minute. But I mean, you're right to be skeptical. They're not super distinct. But you can feel, you'll see in the geometry that there are regions where there's more stretching happening and other places where there's more folding happening. So it's very loose, but it's not nonsense altogether. So I think I'm going to leave that. But okay, but you got that last point, that we're not only explaining or hinting at where these fractals come from, but where the spreading of trajectories can lead to a kind of loss of information. That is, the unpredictability associated with chaos also is inherent in this picture, that this little blob eventually becomes spread out everywhere, and it's hard to predict after the long run where something will be. Okay, so let's try looking at that on the computer now. I don't mean my usual thing with computer animations or numerical integrations. This is going to be some pictures from a remarkable book. Not my book, a different book. And I don't see how you can really take notes on this, but I'll just post the pages on Piazza, or you could look at the book I'm about to recommend. So here we go. This is the book. Let me make it a little bit darker. That's okay? Yeah. Let's do that. Off, really dark. So that's the book I'm going to discuss by Ralph Abraham and Christopher Shaw, Dynamics, Geometry of Behavior. It almost looks like a comic book. It doesn't really have equations in it. This book was written in the, gee, I don't remember now. Might have been early 80s, late 70s. I suppose it was early 80s. And I can remember at the time wanting to find a book where I could learn about this newfangled subject of chaos and strange attractors and all that. And it was hard to find any book that was readable for a beginner. But this book was such an attempt. In fact, it went all the way to not using equations. It just was trying to explain the whole subject visually. So if you're very visual, you might find it an interesting take on our whole course, kind of. So let's focus first on this example that they discuss. Actually, it occurs to me that I probably ought to write one thing on the board before I get into that. Excuse me, I'm going to have to put the lights back on. The object that's being shown on the cover, I should have written the equation for, because I do believe in equations. I want you to know that, but that is to know what the equations are for chaotic systems and how to analyze them, not just the pictures. So this image that's being shown is something called the Rustler attractor. So that's with an O with an umlaut, Rustler. So Otto Rössler is a biochemist who, around the mid-70s, was trying to answer the questions we're asking now. How do you think about the geometry of chaos? What's causing strange attractors to have the shapes that they have? And so he, unlike Lorenz, who was motivated by science and wrote down his governing equations by deriving them from fluid dynamics, Rustler tells the story of going to, I don't know, like a carnival or some kind of a street fair where he saw a machine that was making taffy. Do you know what I'm talking about? There's this goopy, sugary stuff, and then there's these mechanical arms that are going like this and pulling on the taffy and folding it over and stuff. Anyway, so in watching his taffy pulling machine, he got the idea that that was related to the geometry of chaos. And so he wrote down a system of equations just by making them up that would do that kind of geometry, to see if he could make a strange attractor manually just by writing down equations. So he did do that, and he ended up writing the simplest strange attractor that's known. It's simpler than the Lorenz system. In fact, I'd say it's probably the ultimate in simplicity because it only has one nonlinearity. Whereas we remember that Lorenz's equations had two, and the nonlinearity is as simple as it can be. It's just a quadratic nonlinearity. In this case, it's x times z. So his equations look like this. X dot is minus y minus z. Y dot is x plus ay. And z dot is b plus z times x minus c, where the parameters, I mean, none of this means anything physically or scientifically. They're just made up variables, x, y, and z, so I can't give you any interpretation. A and b are parameters that Rustler, I mean, he has various parameter values that do interesting things, but the ones I'm going to show you correspond to a equals b equals 0.2 and c equals 5.7. which you're welcome to simulate on a computer and see what it does. But anyway, it's going to do something very close to what's shown on the cover of the book by Abraham and Shaw. So let me now go back to talking about that. So there they have the attractor. Now, you can see that it looks a little bit like half of the Lorenz system. Can you remember the Lorenz attractor was that butterfly shape where you'd spiral around one wing and then shoot over to the other wing and spiral around there. Here, we just have effectively one wing. Now let me try to say in more detail what's going on there. Let us, let's see what's on the next page. I wonder if I need to make this a little bigger for you. How about we go like this? Ooh, that's pretty big. So you see, so Christopher Shaw is the cartoonist. He's the artist. So these are all just hand-drawn pictures. That's probably a little too big. And I really like them. So in this picture, he's showing the attractor, which takes a while to get used to. What the heck is going on here? Well, you see trajectories with red arrowheads on them. And here they're imagining a blob of initial conditions starting at a time t0. And then watch how it flows around. Maybe, I don't know, maybe it's clearer if I do it with my hand. All right, you start with this blob. And then, you know, like these guys follow this track. Notice we're going up into the third dimension. This helps clarify why 3 dimensions is needed for chaos. Here, this part of the blob is going off in this direction. And as the blob goes up and then gets folded over on this top part and then comes back around, I mean, if you can actually trace in your mind or with your finger this point, you'll see, let's see if we can follow it. So this goes up here, folds over, comes down around, ends up, did I do that wrong? I did it wrong. Yes, I did. Good. I'm glad you can see that. It went actually over to here, didn't it? And ended up there. Except not there. Maybe here after time t1. So this side got mapped over to here, whereas this, if I go up and around, then I spiral around here. Well, I've lost it. Where did it go? It should have gone here, right? It did. Okay, but I couldn't follow it. I'm very embarrassed about knocking the screen. I don't want to make it bad on the video. Anyway, so you can see that the main point was that t0, at time t0, this little ellipsoid of initial conditions, after time t1, it's gotten stretched and a little bit compressed, like we said should happen with the dough. And if you keep going, then this shape starts getting deformed in various ways and spreading out. Now, you might be confused about what's happening back here. That is, it's pretty clear that there's a nice flat-looking surface, but then what's the deal? Is it merging with itself? You know, like is it forming a branch or something? It's drawn vaguely back there. It's hard to see what's going on. So let's talk about that a little more. Let's see. So here they try to explain how you could kind of build up the Rössler attractor in pieces. First, think about a surface on which there's stretching happening. That is, these trajectories are diverging from each other exponentially fast. Take that shape and look at this sequence of operations being done to it. Here was that shape in step 1. In step 2, as you elongate it along the trajectories, you also start folding this little wing of it over until it's all the way like that. And then, continuing, that folded bit wraps around in a circle and gets so compressed that it looks almost like it's sitting on top of itself. And now that part, as it comes around, is supposed to merge into this. But now that's not really possible, right? Because you can't have two surfaces. Remember, trajectories can't cross themselves. And we have uniqueness of solutions. You know, it's the same principle. So you can't have two sheets being glued onto one. That would violate the uniqueness theorem for differential equations. So in fact, where these two are coming around to join, actually, well, let's scroll this up a little bit. How is that possible? I mean, here they show it joining, but we know that that can't quite work. So that requires more explanation. Here's a bit more explanation. In the section they call fractal microstructure, go back to the original shape and start thinking about it more carefully. Here we are again with the one sheet here that has gone around and gotten folded to make two. Now, if you go a little bit farther, that 2 has come all the way around to here, but when it goes around, it will make 4, like I tried to illustrate with the dough. And then that 4, of course, is going to make 8. So up there, it's 4 on the right. By the time it goes around, it's 8. And so the real answer is that the whole time, it wasn't 1 or 2 or 4 or 8. It was always an infinite number of sheets the whole time. And that those infinite number of sheets have to merge in some complicated and confusing way, which they tried to show in this picture in cross-section. So that is, if you slice through the attractor above in what's called the Poincaré section, meaning you cut with a plane through the attractor this way, and then within that plane, if you did yet another cut, which they call the Lorenz section, then you would start to see this pattern of different gaps where the red is intersecting the Lorenz section. You have a big gap here, there's a little gap here, there's a medium-sized gap here. That is, just focusing on the gaps, they get this diagram here of what's happening in the Lorenz section. Big gap, medium gap, little gaps, and so on, with the dots in between being the places where the attractors hit the sections. And they say that reminds them of this thing you may have learned about in some analysis or topology course, where you have a line segment which then has its middle third removed, or it doesn't have to be third, but some middle portion removed to make 2 intervals, and then you keep removing, let's say, to do the classic case, the middle third. If you keep doing that, you'll end up getting a picture that looks sort of like the picture we had above. That is, this is the construction of the so-called Cantor set. And people learn about the Cantor set in pure math, and it's assumed it has no meaning in science at all. But that's totally wrong. It does have a meaning in science. It is a basic aspect of the geometry of strange attractors. So when I once was, fledgling scientist, mathematician, I went to a conference about chemical chaos, and somebody said something about they had measurements of their chemical chaos, and it's the attractor that it made when they plotted their data, and they said this attractor is, of course, a ribbon cross a Cantor set. And I just remember being freaked out by that at the time. What? Why did you say it's a ribbon cross a Cantor set? The ribbon is this surface that we've been talking about that's getting folded, and it's getting folded in a Cantor set way. So they had this picture in mind that I didn't know yet. Maybe I should put the lights back on to rouse anyone who's fallen asleep and ask if there's any question at this point. I mean, there may be a lot of questions. Next I want to talk about the Cantor set for people who haven't thought about it much. But yes?
So it has this little dots in it. So if it was all one sheet, it would remain one sheet, or like one bubble. It would never separate.
The question was, we represented the initial conditions as a cloud of dots, but if it was, say, a disk, continuous,
Or
just a full volume, not just a bunch of discrete dots, then that volume, like a piece of taffy, will be getting stretched. Won't come apart really, but it will be getting stretched out. Yes?
Can we think about iterated mappings?
Oh, good. This question is, can we think about iterated mappings, like, say, the logistic map, using this same way of thinking? Absolutely you can. And so I'll be talking about that more in the next lecture, but briefly, now that you have this idea in your head, you see the logistic map with new eyes. Right? The logistic map had a graph that looks like that. To new eyes, this looks like taking an interval and bending it and stretching it into this shape. That is, imagine a piece of wire, and then I just really stretch it and bend it to make the parabola. So the logistic map the whole time was doing stretching and folding. But we didn't think of it that way. But it was. And it was also doing reinjection in the sense that we chose this map to have its maximum at a value less than 1, so that when we take this whole interval 0 to 1, that is the wire, when we bent it and stretched it, it gets mapped into something here which is still between 0 and 1. you know, that's the reinjection part. Now this is not going to produce exactly the kind of chaos we want because this map is not invertible. So that is to say, if I have some point here, there are two initial conditions that can lead to that same value. And so you don't have reversibility going backwards in time. Whereas with a differential equation, you can always run it backwards in time. So the logistic map is a bit too crude for a model of chaos that we see in three-dimensional systems like the Rustler system. But it has a lot of the right stuff. Yes?
Is that system like a 2D map?
This system is very close to, yeah, we can understand a lot of what's happening here by thinking about two-dimensional maps rather than one-dimensional maps. And so in the next lecture, I want to discuss that. Yeah. Okay, yes?
Can you discuss like elaborate more on how they merge? Because you said it like
the merging. Yes, that's a very hard point, isn't it, to understand how does the merging take place? That is, you thought it was one sheet, but if it was one sheet, as it goes around, it became two. And that will lead you into, I mean, the only way you can get something to merge properly is if it was infinity the whole time, so that after it doubled, it was still infinity. That is, if it was any finite number of sheets, it wouldn't make sense, because the one would have to merge into two or something. So I can't say much more. It's very hard. I mean, we have to think about infinity, which is hard. But I can't really say more than...
So that doesn't mess with the fact that it's unique?
There's no problem with uniqueness. But I think at this point I want to read to you from Lorenz, because, you know, back in 1963 when Lorenz was publishing his paper that, as I said before, was ignored for quite a long time, at least 10 years. Look at this interesting comment in Lorenz's paper. I don't know if you actually read Lorenz like you guys were supposed to. We haven't talked about it much. But look at this amazing remark. So I got to zoom in here a bit. Let's go up to about 200. Okay, so okay, so he's talking about his work, and he says the conclusions that, you know, he's trying to calculate how many periodic orbits there might be and all that other stuff. He says in here, need a pointer. Well, anyway, he says these conclusions. So he's talking about what can he say. He's done this in the computer. And remember, computers in 1963, like I said, have bugs. The vacuum tubes blow out. They're not really reliable. So a lot of his colleagues wouldn't believe what he has. He says they've been based on a finite segment of a numerically determined solution. They can't be regarded as mathematically proven. He admits that. This is not a proof of anything. Although the evidence is strong, but then he notices that there's something that people will see as a contradiction. One apparent contradiction requires further examination. It's exactly your question about the merging of surfaces. He says it's difficult to reconcile the merging of two surfaces. So here now he's not speaking about the Rössler attractor, which comes much later, but, you know, with this motion of I'm moving on this eye of the strange attractor and then spiraling over here and then back. It's difficult to reconcile the merging of the two surfaces, one containing each spiral, with the inability of two trajectories to merge. So they can't really merge. And he says, but it's not difficult, however, to explain the apparent merging of the surfaces. That is, why does it give the illusion of merging? He says it's not really merging. He says it's only apparently merging. And he explains why, and he then does the calculation about volumes occupied by what he calls a specified set of particles. That is, he's imagining the blob of initial conditions. He does the calculation we did actually several lectures ago, where we showed volumes shrink exponentially fast in the Lorenz system. So here he writes that the volume at time t1 is some exponentially shrunken version of the volume at time t0. And then he does a calculation. He says it takes 70 iterations using his time step, so that after you go once around a spiral, I guess I got to go back up here, the volume has shrunken to this amount of its original volume. It's way down. You know, what is that? 7, I don't know, times 10 to the minus 5, it looks like. So two particles can therefore come together very rapidly and just appear to merge. Okay, now comes the part that I love the best. Listen to this amazing paragraph. He says, it would seem then that the two surfaces merely appear to merge. and remain distinct surfaces. Following these surfaces along a path parallel to a trajectory, like we did in the cartoon, and circling those fixed points, we see that each surface is really a pair of surfaces. So that where they appear to merge, there are really 4 surfaces. Continuing this process, we see that there are really 8 surfaces, etc. And we finally conclude that there is an infinite complex of surfaces, each extremely close to one or the other of 2 merging surfaces. So this phrase, the infinite complex of surfaces, is how he's, this is long before anyone has talked about fractals. He knows what's going on. He has everything that we've said in this course, except that you can imagine his colleagues reading this, if they even bothered to, having no idea what is he talking about. Right? It's not very clear. Although it is, in retrospect, it's perfectly clear. But he doesn't draw a diagram. He can't. He has no computer graphics. But he sees it all in his head. This is how great Lorenz was. Anyway, there's a million more great things in the paper, but that I really do like that. So now that doesn't really answer your question any better than I did, but that's what's going on. There's this infinite complex of surfaces. Now the next lecture, when we talk about something called the Hainan map, a 2-dimensional map, maybe you'll at least be convinced that this is really happening, but it's still hard to quite visualize how. Yes? Okay, the question was, there's a dimensionality associated with this strange attractor that's a little bit greater than 2. It's been calculated that the Lorenz attractor has dimension 2.05. So it's a little more than a surface, but less than a solid volume, which would have dimension 3. So what can that mean? And yes, it's related to it being a so-called thick surface. It's thicker than a surface. It has a dimension more than a 2-dimensional surface, but it's not as thick as a solid volume. So, that requires some explanation, and so let me get to that kind of idea by talking about the Cantor set, which is probably the best place to start talking about fractal dimensions. Anyway, all right, so that's Lorenz. Let's go back now to the board. So I can't really calculate for you this dimension 2.05. We can discuss later how that was calculated, but I can do a simple exact calculation of the dimension of the Cantor set. So let's talk about that first. The Cantor set, as we said, you should think of this way. You take a closed line interval, let's say from 0 to 1. When I say closed, I mean it includes its endpoints. Take that, then delete the open middle third. So the next step, it would go from 0 to 1/3. And I keep the 1/3, right? So it's a closed set. And then over here, I keep the 2/3 and the 1. But I've knocked out the open set from 1/3 to 2/3. And then keep doing that, always knocking out open middle thirds of whatever remains. So at the next stage in the construction, it would look like this. Now Cantor, in the late 1800s, or early 1900s, I don't remember, is doing this kind of thing for his own reasons. He's not studying strange attractors or chaos. That's not a concept that's out there yet. Not really. Poincaré had done some work, but Cantor is not motivated by anything that Poincaré did. He has other reasons which we won't go into for looking at this complicated set. And anyway, he keeps going. Let's think of it as a series of stages. Let's call this one, I don't know, this is set S0, this is S1, this is S2. And imagine going on down to some limiting set S infinity, which I won't dare to draw. But that set S infinity is the Cantor set. Not usually called S infinity. I don't know what we should call it. Let's call it C for Cantor. So your first thought might be there's nothing left. Right? There's nothing there. But that's not true. There's a lot there, actually. Can you name some points that are there? 0 is there. I never take out 0. In fact, I never take out an endpoint. Right? So all these, so 0, 1/3, they all survive all the way down. And so do all the other endpoints created at any stage. So it certainly contains all these endpoints. Now, some students think, when they first meet this, that that's it. It's nothing but endpoints. In which case, the Cantor set would be what we call countable. You can show that there's only a countable. I mean, we could actually count how many endpoints are there at each stage. 2, 4, 8. So it looks like the number of endpoints at any finite stage is 2 to the n at the nth stage. But still, okay, so that's going to infinity, but it's not an uncountable infinity. It's not the same as the infinity of the real numbers. So now, I know a lot of students don't have background in countable versus uncountable sets. If you're from an engineering background, you might not have thought about this before. So the book has a whole discussion about countable versus uncountable, if you've never learned about that. And I could talk about it, but I don't think I want to talk about it right now. If you want, we can discuss it. But let's just leave that for now, this issue of countable versus uncountable, and try to talk about what's meant by the dimension of this set. So here are some of the key properties of the Cantor set. First of all, it has a total length equal to 0. I'm really sort of fudging because I'm not trying to do a pure math course on real analysis here. Really, the word should be measure, not total length. I mean, it has measure 0 in a certain precise sense that you could learn in a course on measure theory. But for us, let's just think of it in this crude way that imagine we do a naive calculation where we say, well, the length of S0 is 1. Let me use this symbol for length. So the length of S0 is 1. The length of S1 is 2/3, because it's 2 intervals of length 1/3. The length of S2, well, each of these is length 1/9, right? This goes from 0 to 1/9. They're all congruent. There's 4 of them. So this is actually length 4/9 in total. But a more clever way to think of it is that it's 2/3 squared. Because it's at each stage, you take whatever the length was, and then take 2/3 of it to survive. 1/3 you've knocked out, right? The middle third was lost. So at the nth stage, by this kind of reasoning, the length of whatever is there will be 2/3 to the nth power. And you can see that as n goes to infinity, that goes to 0. And so that's the sense in which I mean that the Cantor set, to the extent that it makes sense to say it has a length, its total length, it can be, we could say it this way, it can be covered by intervals whose total length goes to 0. So there's very little stuff there. It doesn't contain any intervals. Right? I mean, if it contained an interval, it would have a length. Total. It does not contain an interval, even an arbitrarily small one. Any question about that first point? Okay, so total length of 0. Yet, it has an uncountable number of points. Well, that's a funny way to say it. It's uncountable. That is to say, it can be put into a one-to-one correspondence with the real numbers. So it's as numerous as the whole original interval. This is really paradoxical. That is, there are as many points in this interval, 0 to 1, as there are in the Cantor set, even though you've knocked out so many of them that now has length 0. It still has the same amount of points. Hard to think about how that could be, but it's true, and we could give a proof of it. The book, in the book, I show a nice argument, but it requires thinking about base 3. So the Cantor set can be shown to consist of all points in the interval 0, 1. Closed interval 0, 1, whose base 3 expansion can be written solely with 0s and 2s. They have no 1s in their base 3 expansion, these points. Let me come back to that if you're curious about this. It's interesting, but I do want to jump onto this point about dimension first. It's a self-similar set. That's the third property I want to mention. So this is jargon that you hear in connection with fractals. Set is self-similar in the sense that it contains arbitrarily small copies of itself. So by that, I guess I mean something like, if you look up at any one of these, well, if you went, I don't know. Here's one way to see what I'm saying. Let's look again at the picture in this construction process. Okay, so here I'm showing S0, S1, S2, S3, and then somehow, mysteriously, down at the bottom is this limiting set S infinity, the Cantor set. But rather than trying to think about the Cantor set first, just think about what's happening at some finite stage. Like, suppose you look at the left half of S2. Look at that part. Okay, what's the structure of that thing that I've just circled? Well, it looks just like the thing above it. It's got two intervals separated by a gap, except it's a scaled down version. If you were putting it on a reducing photocopier, you would say that if you take S1 and shrink it by, well, I don't know, shrink it by a factor of 3, by the way, is that clear? Why do I want a factor of 3? Remember, this goes from 0 to 1, whereas this goes from 0 to 1/3. So if I put this on the machine and set it at 33.333%, then when I make the photocopy, this will shrink down to fit exactly on there. And it's shrinking it in both directions, but in the vertical direction, it's a line I mean, it's got no thickness anyway. So we're shrinking it by a factor of 3 in all directions. So start with S1, shrink it by a factor of 3, and then you get the left half of S2. And so what? That's actually true all the way down, right? That is, if I took S2 and shrink it, that is the whole of S2, shrink it by a factor of 3, I'd get the left half of the one below it. And then, at some point what we want to do is go all the way down to S infinity, where the statement would be, take S infinity, shrink it by a factor of 3, you would get the left half of S infinity plus 1, meaning S infinity. That is, the left half of the Cantor set is just a shrunken down version of the whole Cantor set. And not just the left half, but any little piece of it is a shrunken down version of the whole thing. So that's what I'm trying to say when I say it's self-similar. It contains all these various copies of itself at different scales. So similarly, from this, the left half of S infinity is shrunken version of S infinity. I'm being loose, but I think you get the idea. Do you want to ask anything about that? Yes?
Is that entirely uncountable? Or can it have this property and still be countable?
Could a countable set have a property like this? That's an interesting question. I don't know the answer to that offhand. I don't know. I can't think of any fractals that are countable. But I don't want to say I don't know. It's an interesting question. I sort of think you might be right. That does imply that, but I don't know. But let me get to the dimension, which I wanted to do before we run out of time. That is, I've set this up with this remark about self-similarity, and now we can say what we mean about the dimension of the Cantor set, which is that, so we're doing properties of the Cantor set, and in addition to being self-similar, it has what people call similarity dimension, but let's just say dimension, log 2 over log 3, which comes out to be about 0.63. So the dimension of the Cantor set is between 0 and 1. It's not zero-dimensional, which would be the dimension of a single point or of a finite collection of points. Or actually, I suppose, probably of a countable collection of points. Is that true? I'm not sure about that either. Do the rational numbers have dimension 0? I don't know. I have to think about whether countability always goes along with dimension 0. But in any case, this set has dimension between 0 and 1. It's not the dimension of a curve, which would be 1, or a line. It's in between. Now, why would we say that? OK, so the dimension, we have to think about what's a sensible definition for dimension of self-similar objects. This is a whole big subject, and I'm just trying to give it to you in a couple of minutes. But so there's many different notions of dimension. And this is just the one that's easiest to do right here. You may have heard about dimension in terms of number of coordinates you need to specify a location. Like we say the world is three-dimensional because, to specify the location of this, I have to give you its height above the ground, its distance from you that way, and its distance from the wall this way. So 3 numbers specify location in three-dimensional space. That's the usual way of saying it. But how would you specify location in the Cantor set? You could just give 1 number, which is distance from the origin. So you might say it's one-dimensional. But that's really not the best definition of dimension. It doesn't really generalize well to these fractal objects. It doesn't distinguish various fractals that you would want to distinguish. So the way that people define dimension in this context, and it reduces to the ordinary dimension for things that are not fractals, is they say, like, let's think about something like, say, a square area. Okay, now you could sort of view a square area as self-similar in the sense that if I reduce it, let me use a factor of 3 to make a connection with the Cantor set. So let's suppose we reduce by a factor, we'll call it r, which is 3. And I mean in all directions. Then, you know, I'm going to get a small square. And if you compare it to the original square, you'll see that 9 of them will fit in there. Obviously. Right? If you shrunk it by 3, then there'd be 9 copies of the reduced one. Nine copies of the reduced object make the original. And now what is this 9? Well, 9 is related to 3, because what if I had shrunken it by a factor of 4? Then I would need 16. Right? Or if I shrunk it by 5, I would need 25. The rule is that whatever my shrinkage factor is, the number of copies I would, I mean, assuming it fits in nicely into the original square, then I need, if I shrink by r, I'm going to need m equals r squared copies. Plausible? That 2 is the key. The 2 is reflecting the dimensionality of the square area. This is a two-dimensional shape because this 2 appears in the exponent. I mean, or maybe I should say it the other way. The 2 appears in the exponent reflecting the two-dimensionality of this shape. So the generalization that people use for self-similar objects that aren't as simple as a solid square is they say, if I have a scaling relation m equals r to the d for my self-similar object, I'm going to call d the dimension, or technically the similarity dimension. So if we apply that to our Cantor set, well, we said a couple minutes ago that if we take the Cantor set, shrink it by a factor of 3, then what would happen is, as I discussed up here, if I shrink in these finite stages, if I shrink the line above by a factor of 3, I get the left half of the line below. So with the Cantor set, if I shrink it by a factor of 3, I will get the left half of itself. And so that means that when I have r equals 3, I have m equals 2. That is, 2 copies of the threefold shrunken Cantor set make itself. And so feeding that into this formula, m equals r to the d, let's solve for d. I mean, you could take log of both sides. You get log m is d log r. So the dimension is log m over log r, which for the Cantor set would give us log 2 over log 3. So this is why people say that it's got this fractional dimension. And you can apply this kind of calculation to other self-similar objects, and it's interesting to see what they come out to be. So there are various examples of that in the book, in the fractal chapter. But I hope that gives you at least a flavor of this. You should do more reading on your own. And then next time, I guess I want to talk about the two-dimensional map that we mentioned earlier, the Hainan map, to understand more about this stretching and folding and how that implies fractal structure. We still haven't really seen it numerically. We haven't seen it in the Lorenz system. I didn't show it today. But the Hainan map will really, I hope, prove it to you that these ideas do work. OK, so let's quit for now. Thanks.